Welcome to this video, where we're going to break down supervised learning, one of the most important foundations of machine learning. Whether you're building a spam filter, predicting stock prices, or diagnosing diseases, supervised learning is probably behind it. Let's jump in. Supervised learning is exactly what it sounds like: learning with supervision. We train a model on a dataset that already contains the correct answers. These are called labels. This method powers about 80% of real-world ML systems, and it comes in two flavors: classification, where we predict categories, and regression, where we predict continuous values. Let's say we want to train a model to recognize cats in images. We give it a bunch of labeled images, some with cats, some without. The algorithm learns to associate certain patterns with the label cat. It's just like teaching a child with flashcards. The model maps inputs to outputs, learns the pattern, and eventually starts predicting for new, unseen data. Classification is about assigning labels. Is this email spam or not? Is the tumor malignant or benign? This is ideal when the outcome is discrete. Some of the most common classification algorithms include logistic regression, decision trees, support, vector machines, and neural networks. To evaluate them, we use metrics like accuracy, precision, and recall, which we'll touch on later. Let's take it a level deeper. Decision trees are great for interpretability. SVMs handle complex boundaries. Random forests reduce overfitting using an ensemble of trees, and neural networks shine in high-dimensional data, like images and text. Each one has its strengths, and choosing the right one depends on your data and problem type. Now let's talk about regression. Here, we're predicting numbers, like house prices, temperature, or sales forecasts. The key is the output is continuous, not a category. Most popular regression models: linear regression, polynomial regression. And when accuracy matters, we use metrics like mean squared error, MSE, to evaluate how far our predictions are from reality. There's more to regression than just straight lines. Linear regression is simple and fast. Polynomial regression captures curves. Ridge lasso handle multicollinearity. And SVR is great when your data has outliers or noise. Choosing the right method helps avoid underfitting or overfitting, which are common beginner traps. No ML journey is complete without validation. You don't just build a model, you test it. We split data into training and testing sets using train test split or cross-validation. Common metrics R squared tells us how well the model explains variance MAE and RMSE, tell us how close we are to the actual values. We also tune hyperparameters to improve results without overfitting. Where is supervised learning used? In healthcare, to diagnose diseases early; in finance, for credit scoring or stock predictions; in e-commerce, to forecast customer behavior; in manufacturing, for predictive maintenance. It's all around us, but it's not all sunshine. Supervised learning depends heavily on high-quality labeled data, and labeling is often expensive or time-consuming. We also face bias in training data, fairness issues in sensitive applications, computational complexity as data grows, and the need for continuous model updates to handle change. Ignoring these can lead to models that are accurate but dangerously wrong. So, where's this all going? We're now integrating supervised learning with deep learning to boost accuracy and handle unstructured data. There's a strong push for more interpretable models, automated feature engineering, and ethical AI that's fair, transparent, and responsible. As tools improve and data grows, supervised learning is becoming even more central to intelligent systems across every industry.